Okay, so let's start with the first lecture that is a high-level overview of the whole course. And then this is the structure of this lecture. So why you need optimization, different kind of optimization problems you have. I have already mentioned some of them, linear, nonlinear, integer, combinatorial. For each one of these kind of problems, we'll use different techniques. And then at the end, optimization is a mathematical problem. So you have to formulate that problem properly. So you have to give what is the objective function that you want to minimize or to maximize, to add constraints, which are the variables that you can tune. And then we will see in this lecture what is the condition for having a minimum, and also a little bit when a function is defined on multiple variables, that is called multivariate calculus. You are familiar with a univariate calculus with only one variable, that maybe not so much with multivariate. Then these two techniques, they are extremely important, least squares and pseudo-inverse, and we will see a couple of results that are very well established here. Then the concept of iterative algorithm. So sometimes you can give the solution of an optimization problem in only one step. That is, for instance, the case of the least squares. But very often you prefer some approaching the solution in an iterative way, because you don't know how to go directly to the global minimum. And one of the most well-known techniques for these iterative algorithms are this gradient descent, and then we will see some mathematical facts about optimization. Okay, so why optimization? So we have already introduced a few of the problems that you can see. So in real life, every time you ask yourself, what is the best way of doing something, the word best implies there must be some optimization, and there must be some optimization of something concrete. So you have to specify best with respect to what. So you have to say with respect to what quality function you want to be the best. And whenever you train a model, machine learning, for instance, as you were doing last year, or you have to find the parameters of a model or select features to train the model, you are solving an optimization problem. And for instance, in linear regression, you know what linear regression is. So probably it's useful to have some drawing. So linear regression, you are given a set of points. So let's do it in one dimension. That is easier. So you have some predictors, some predictor variables, and this is the output for the input. And you have some predicted variable, and this is the output. And you are given some pairs, so you are given some points. And let's say that there's a nice relationship between the two, and then you are trying to find this line. So this line is defined as the output as a function of the input. So if you have an input value, let's use a different color. So you have an input value here, x0. You want to see what is the predicted value, predicted hat is predicted. So what is the estimated value for this one? And maybe you have some point there, so there will be a difference between the truth and your prediction. And you want to minimize this difference. You want to minimize this difference for all points that you have observed. So do that for all the points you have observed. And you want to minimize that with respect to the parameters that you can tune. You can tune A and B. So minimum with respect to A and B. So you want to find the A and B such that the difference between your predictions and the observed values is as small as possible. That is the least squares. Actually, this problem is least squares. And you see we have not been very creative about the names. So squares, because we have squares, and least these because we have minimum. Okay, so that is what we want to solve. Okay, so when you minimize the error between the predicted and the actual values in linear regression or any kind of regression, that what you are doing is minimizing the error with respect to the parameters that you can tune. In neural networks, it is the same, only that the error typically is something more general called a loss function that can be least squares, but can be complemented with many other things. And then instead of just tuning two parameters, you have millions of parameters that you can tune. When you're doing clustering, in clustering, you're also minimizing the intra-class distance, so the distance between the objects assigned to the representative of that class, and maximizing with respect to other classes or to other clusters. Or when you are doing dimensionality reduction, do you know dimensionality reduction also? For instance, PCA, principal component analysis. Again, you are maximizing something that is the explainability or the amount of information kept by a discrete number of variables. So in all data problems, there is always an optimization problem behind. So without optimization, you can have a solid mathematical way of finding the parameters that you need to learn, to do inference, to do decision making. Okay, so if it is an optimization problem, so if it is finding a minimum of something, so we can try to give a very general formulation of the problem. So I think this is one of the most general formulations, that is minimize a function subject to some constraints. And these constraints can be inequality constraints or equality constraints. Okay, so the constraints will give you something called the feasible region. So the feasible region is the set of points in the input space. So here I'm using X for the input. Yeah, and in this example, it is I took the figure from somebody else. So why here it is not the output? The output would be f of x and y. So x and y both are inputs. So what is the region in the input space that satisfies the constraints? That is the feasible region. And then within this feasible region, you evaluate the function for all points, and then you decide which one is the maximum, the minimum. And there is actually a comment. Any optimization problem can be put in this framework because maximizing is the same as minimizing minus f of x. So if I want to maximize something, it is the same as minimizing minus f of x. So at the end, all problems are minimization problems. And then here it is just a summary of what I had just said. So X is the input space. So those are the variables that you can decision variables, if you want. So the variables that you can choose to get to the maximum or the minimum of that function. Then f is the objective function, also called the goal function or the loss function. It depends on the context. And then you have the constraints. Some of them are inequalities, some of them are equality. And this nomenclature of G and H is rather standard. So most optimization books, they talk about G and H for the constraints and F for the objective function. Yeah. Okay, so This is a summary of all kinds of optimization problems that we will cover. They are the most standard ones. So I'm making sure that there's some strange case that is not covered here, but most of them, more the useful cases are here. And we will see each one of them one by one. So the first one is linear programming. By the way, in the mathematical literature, optimizing is also called programming. So when you have linear optimization, that is also called a linear program. So, for instance, let's say, let's first give an example of where these kind of problems could appear, and then we will formulate it as a linear program, as a linear optimization problem, and then we will give the more general structure. So we will always follow this path. So first an example, then trying to formulate that as a problem, and then generalizing. Okay, so let's say that you are the manager of a factory, and this manager, this factory produces two products, A and B, and then A requires 2 hours of machine time and 3 units of raw material, and B can be manufactured in the same machine. It only requires 1 hour and it needs 4 units of raw material. So both A and B can be manufactured from the same raw material. You have per week, you have 100 hours of machine time, and you have 240 units of the raw material. And the profit of selling one A product is $40 with, and the profit of selling a B unit is $30. So the problem here is to maximize the profit while staying within the limits of your resources. So your resources here is machine time and raw material, so which is the optimal production that I could have, so that my benefit is maximum. Okay, so let's say that I have to define 2 variables that I can act upon. So one of them is the number of A product units, and X2 is the number of B units. Okay, and then what I want to maximize is the profit. So I have to write this profit as something I can maximize. So it is maximizing 40 times the number of A units plus 30 number of B units, and subject to some constraints. So every A unit requires 2 hours of machine, every B unit requires 1 hour of machine. So it must be that 2x1 plus 1x2 must be smaller than 100 hours. And then the same for the raw material. So 3 times the A units plus 4 times the B units must be smaller than the total amount of raw material I have available per week. And then there is an extra constraint, that is that X1 and X2 have to be non-negative, because otherwise it would be a solution that doesn't make sense. So in general, a linear program is something that can be formulated in this way. So it is a vector T transpose X. So X is another vector subject to some equality constraint and some inequality constraint. So this is the standard form of a linear program. And X is the variables that you are acting to in order to have the maximum. C here it is a cost vector, and you want to minimize the cost. And A is a constraint matrix, and B is the right-hand side vector of the constraints, of the equal constraints. And yeah. So here I have I am maximizing something. In the general form, it is minimizing, but this is very easily interchangeable because all I have to do is to minimize minus this thing. So I want to minimize minus 40x1 minus 30x2. And so converting maximization to minimization is very easy. Then we have these constraints that we don't know yet for the moment how to translate into equality, but I'll show you in a moment. And then what else? Yeah, and this is of the form that we request for linear problems. So linear problems must be a vector times x. So I want to minimize, let's do it here. So I want to maximize, I have to define x1 and x2. Typically also you put a star for the solution, and then you say there are arguments that maximize with respect to x1 and x2, this thing, 40x1 plus 30x2. And then this solution is the same as the argument that minimizes with respect to x1 and x2. Then I will write it like this: minus 40 minus 30 transpose x1 x2. For us, all vectors are column vectors. So then if I write them like this, they are column vectors. If you want to be very, very strict, and you can say something like this. But as long as it is clear from what we are writing, that it is correct. But in general, all our vectors are column vectors. So this would be C. This is C transpose, and this is X. And normally when I write in the whiteboard, I use bars for this. Okay, so it is a minimization problem. It's a minimization problem. How to handle these constraints that for me they are inequality constraints, but in the general form, I only have equality or x larger than 0. So how to transform that? And this figure here, it is this C transpose X is the equation of an hyperplane. So it is an hyperplane in the dimensions of X. So X here in this example is 2 dimensions. So if you consider also the output, you are in a 3-dimensional setup. So C transpose X is an hyperplane in that 3-dimensional space, and that also happens with lines. For instance, so this line here, if you consider the input and the output, these I can write in this way. So I can write that equation. I can write it in this way. So I can say A minus 1 xy plus b is equal to 0. So this is of the form, again, this is of the form C transpose X. Now X is a vector that collects X and Y. This is a vector, that's b equals 0. That is the equation of an hyperplane. Hyperplanes in 2 dimensions are lines. So it is something that is straight and has 1 dimension less than the space where you are acting. So this is 2 dimension. So this is 1 dimension. Okay. And if you are in 3 dimensions, this one, so if you consider X, Y, and Z, C transpose X plus B equals 0 is an hyperplane. It's an hyperplane, so that is something straight in a 3-dimensional space, and it has 2 dimensions. that is a plane, 3 dimensions. An hyperplane is a plane. It's the standard plane. But if you are in 20 dimensions, this is the equation of a 19-dimension plane, and in that 20-dimensional space. Okay, so this is the equation of an hyperplane, and here we have the feasible region. So an hyperplane is something that extends to infinity, from minus infinity to infinity. So here I have the feasible region. So I'm drawing here the feasible region in this way. And then within this feasible region, for every point in the feasible region, I can evaluate the function, so the result, that is the result of the hyperplane. So one of the characteristics of linear programming is that the solution is always in one of the borders of this hyperplane, intersected with this kind of cube or whatever of the feasible region. So it must be in one of the corners of the feasible region. Okay, good. Then, how to convert this kind of inequality constraints into this standard form? So for us, it is more natural to write, for instance, and we did it in the previous case. So it is more natural to write the constraints in this way. But we said that the general formulation is this one. So this one is using equalities. This one is using inequalities. So how can we transform an inequality problem into an equality problem? And the trick is to use something called a slack variables. So I will introduce, I will extend the problem to include some other variables that are this slack. That is the difference between, okay, so let's say that in this constraint, in this problem that I have here, my solution, my best solution is using 90 machine hours. So it's using 90 machine hours. So this part will be 90, and 90 is smaller than 100. So I'm safe there. Okay, good. But then there is a difference between 90 and 100. There is a difference of 10. So this then will be the slack variable. So the slack variable will be one such that when you add it to the constraint, you get to the limit. And this slack variable will be always larger or equal to 0. And now I can rewrite my original problem in this way. So I can say I have to minimize this thing that is the same as before, subject to my constraint. Before we had AX smaller or equal B, but now with this S are the extra capacity that I'm not using, these 10 hours of machine that I'm not using, and multiplied by the identity matrix, because you see in all these constraints, the coefficient in front of S is 1. So for all the constraints, what I have is 1 times my S. So this is what I have here. So, and then my constraints are X larger than 0, S larger than 0. Yeah.
It could be like my slack variable 5. So instead of.
Can take any value. Can take any value.
And is it better to make it like closer to the limit or to?
The best is that you maximize your goal function. So you have to look for what is the S and what is the X. So actually, you don't fix S. You have to look for it too. So now before you have to look for the X. Now you have to look for the X and the S. So now I only have equality constraints. So the general form of the linear program is this one. So, and it is called the standard form of the linear program. Okay, so Is this important? Well, aside from the mathematical tricks and so on, when you try to use a library, for instance, a Python library to solve a linear problem, very often the only works with a standard form. So there is no way that you can provide inequalities. It depends on the library. But sometimes they only work on one kind of problems. And sometimes they offer the two, and then internally they use these slack variables. But so you need to know that these things exist. Any question up to here? Okay, good. Then let's move to the next kind of problems that are non-linear problems. Okay, so linear problems could be formulated. So the linearity mostly is here. So we refer to the linearity of the goal function. Here, the non-linearity also refers to the goal function. Okay, so let's say that I want to manufacture, design a cylindrical tank that holds a given volume using the least amount of material. So I want to construct the cheapest tank that can hold, for instance, 1,000 liters. Okay, so how do I design this tank? This is a very classical problem. So, okay, what is the surface? What is the amount of material that I need? The amount of material is proportional to the area of that tank. The larger the area, so at the end, all you have to put is construct these areas and these surfaces such that they hold 1,000 liters. Okay, so then let's measure the area. So the area is the area of the two top and bottom surfaces. So the area of one surface is PR squared, and because we have two, it is 2 PR squared. And then the surface of the wall. The surface of the wall is this thing, 2 PR times H. So far so good for this one. Okay, and now I have to minimize this with respect to R and H. But there is some constraint. So the constraints are that they have to hold a given volume. So the volume of the whole thing has to be something given. The volume is this thing, PR squared H must be equal to V. And then R and H have to be positive. Otherwise, they don't make sense. You cannot construct that tank. Okay, so now if I look at this function is nonlinear. And it is nonlinear in two ways. So the two terms are nonlinear. This R squared is obviously nonlinear. And RH, so the product of two variables is also nonlinear. So the 2 pi is linear. So the 2 pi is a constant, so we don't care about that. But R squared or RH, they are nonlinear terms. So that is why this kind of optimization is called nonlinear programming. So again, the most general formulation of a nonlinear program is this one. So you have to minimize something with respect to some inequality constraints, G, and some equality constraints, H, and then some, and the X are continuous variables. Then, if you imagine this is X, so this tries to represent the X, and here two-dimensional. So we have 2 dimensions. For the previous problem, it is fine because we would have R and H, so the radius and the height. And then for each combination of radius and height, you would have a value of the goal function. So for every R and H, you would have a given area. So you can draw that area. This is not the drawing of the area. This is just some fun function that is beautiful. But then the thing is, there must be a global minimum. And can I find the global minimum? And there are two ways for finding that. One is directly, I just tell you, okay, given this function, the global minimum is this one, or iteratively. You start somewhere, and then you iteratively change your solution until you reach the global minimum. We will see the two kind of approaches. Any question up to there? No? Okay, so let's introduce a new problem. That is, let's say that we want to optimize the scheduling of people, of the staff. So for instance, let's say that the hospital needs to schedule nurses for night shifts over a week. Each night requires at least 3 nurses. The hospital has 7 nurses, and each nurse can work at most 3 nights per week. So the goal is to assign shifts so that the weekly workload is distributed as evenly as possible, and all coverage requirements are met. So this is the goal function that we will need to see how to formulate that. These are the constraints. Okay, so the goal is to minimize the maximum number of shifts assigned to any nurse. So let's say that we define some variables that we will call xij. So xij will take value 0 or 1, and takes 1 if the nurse I is assigned to the night j. Okay, then what is the total number of shifts assigned to a nurse? So the total number of shifts assigned to a nurse is the sum over all days of the week for that nurse. And that we will call it the workload of I. And then W will be an auxiliary variable representing the maximum number of shifts assigned to any of the nurses. Okay, so then we have now our problem. So we want to minimize the maximum load of any one of the nurses, constrained to all the, or subject to all the constraints that we have. First, at least 3 nurses per night. So how do I express that? So for every night, if I sum xij for all the nurses for the night j, that has to be larger or equal 3 for all days. Then the upper bound for each nurse, that is, if I now, instead of summing by nights, I sum by nurses. Actually, this is, did we have 7 nurses? I don't remember. Yeah. Okay, so if you sum for all nurses, the workload for that nurse over the week, that is this sum, has to be smaller than 3. And then W has to be has to be smaller. So the workload of each nurse has to be smaller than this number W that we have chosen, or that we are trying to minimize. And then there is another constraint, that is these xij variables, they can only take 2 values, 0 or 1. So note that this is what makes this problem different from all the others we have seen so far, because now xij cannot take any values. Here in the nonlinear programming, x could take any value, any. So it could work or have any 0.5 if you want. But no, you cannot. Either you work for the whole night or you don't. So now it is the solutions have to be integer values. And that is what makes this problem different. Actually, this kind of problems, integer programming problems, they are much more difficult. They enter into a category called combinatorial problems. So you have to, the search of the solution is much more painful. Yeah, then the general formulation. So minimize function subject to inequality constraints, equality constraints. The variables have to be integers, or some of the variables have to be integers and some others may be continuous. Another question? So let's make a break here, 10 minutes. Well, the name, before I mentioned linear programming and non-linear programming refers to the linearity or non-linearity of the goal function. Here the name is coming from the variables, from which are the which is the nature of the variables that you can optimize. And we have seen that in the general integer programming problem, you can have a mixture of integer variables and some non-integer variables and continuous variables. Okay, then combinatorial programming can be seen as a particular case of integer problems. So not all integer problems are combinatorial, but all combinatorial are integer problems. So let's give an example first. So let's say that you are a salesperson that has to visit n cities exactly once and return to your hometown and try to minimize the traveling distance. So let's say that you're starting in this city here, and then you have to visit all these cities. And how would you, which is the order in which you would visit them so that the traveling distance is minimized? And here, the objective, you have to formulate that in a way that can be solved. So one possibility to formulate it is this way. So first, we will consider the cost or distance of traveling from city I to city J. And then we will encode xij that takes value 0, 1, if it takes 1, if you go from I to J directly. Okay? So between these two cities, xij would be 1, between these two will be 0. Okay, so then what you want to minimize is this. This is the sum over all Cij combinations times Xij. So this cost has only to be considered if the corresponding X is 1. Otherwise, you don't have to. And then you sum over all I and all J. And you have to be careful that J has to be different from I. Actually, this is an extra constraint you may have, but if you set Cij to 0, then it doesn't matter if you travel from one city to itself. But yeah, in general, you don't want to this kind of degenerate solutions. So you consider I different from J, and then it goes from all I's to all J's. This is this double sum. And you only have to consider that cost if you are traveling from I to J. Okay, good. So that is what we want to minimize, which are the constraints. So the constraints is that you have to enter into a city and leave a city only once. So that means entering into a city means that for all I's or leaving a city is for all I's, the sum over J's has to be 1. And entering into a city, for all J's, the sum over I has also to be 1. So these two constraints, what they say is that in each city, you must enter once and leave once. You cannot enter once and leave twice, for instance. That is not feasible. And then there is a problem. If you leave your constraints here, there might be a solution that is just creating cycles. So you might create some cycles, and these cycles are disconnected. So to avoid this disconnection, you have to put an extra constraint. And these are more difficult to understand, but some clever people have shown that one possibility is to formulate it in this way. So you use some auxiliary variables, ui, but they will go for 2 to n. So u1 doesn't exist. You don't need a u1. You only need from u from 2 to n, and there are n cities. And this UI have to satisfy these constraints. So UI has to be between 1 and n minus 1, and UI minus uj plus n xyj has to be smaller than n minus 1. So somehow these two constraints that don't come natural. Okay? So don't try to interpret them in a natural way, but these two constraints prevent having these disconnected cycles. And a few comments here. So the first one is that you use this technique of using auxiliary variables have appeared already twice. So first with the slack variables, in which we had this scenario, so no use machine. So this is very common in optimization. You use some variables that were not originally in the problem, but you introduce them to help you to solve the problem. That is one thing. The other thing is that it is a special case of integer programming. So my variables that I can touch is xij. This xij only can take this value 0 or 1. So this is an integer programming problem, but it has a very special structure. So it has a structure in which the feasible set is very well. It has a very well-defined structure, so it is not just a wide region and you can take any point there. So this feasible set, for instance, the difference between a set that is a structure and a set that is not a structure would be this one. I don't mean that this is the case for the salesman problem, but these two regions, let's say that we have x1 and x2, and this is the feasible region. So this feasible region, you can take any point there. It is a very unstructured set. And let's say that you can only take a point along this path, which is kind of similar feasible region, not exactly the same, but it covers more or less the same area. But it has a very well-specified structure. So in the black neighborhood, you can go from any point to any other point in the neighborhood. In this blue region, you can only travel along these paths. Okay, so that is the meaning of extraction. I don't mean that this is the case of the salesman problem. Okay, but this is the meaning of a structure set. So for these problems, in which integer programming problems, in which the feasible set has a very high structure, typically they have been approached with this combinatorial programming. Combinatorial programming means you have to try all possible cycles. So you have to think of in the most general case, you have to think of all possible combinations of paths. And for every path, you have to evaluate this one and you take the minimum. That is the sense behind this combinatorial optimization. And you can imagine that imagining all possible paths can be very hard. So it can be, especially if the number of combinations is very high. And actually, that is now being, so combinatorial problems in general, they are NP hard. Have you heard this before? The complexity of an algorithm being NP hard. So in general, they explode as the number of combinations, so as the number of nodes grow. So yeah, and we have given a mathematical formulation of this problem, but actually this particular problem has been approached from many different directions, and some of the directions do not use any mathematics at all. So they give you some algorithm, they tell you, okay, so you start in one city, and then you have to try this, and then you have to, and they give you an heuristic. So the heuristics are ways to try not to explore all possible combinations, but sensible combinations that will lead you to some useful solution that is not guaranteed to be the minimum, the global minimum, but is useful enough. And that is the meaning of these heuristics. And the algorithms, these algorithms, they were not originally designed to optimize, not to optimize something in this sense. Okay? So we have formulated the problem in a pure optimization setup. But these are other algorithms that to approach this particular problem and many combinatorial ones, sometimes they are not fully formulated as an optimization problem. Not a question.
So this kind of problems can always be seen like from a graph perspective.
Most of them, yeah. Combinatorial problems, typically they can be approached through graphs.
Like finding a Hamiltonian cycle that covers all the variables.
Yeah.
And all that stuff.
So in general, yes, I'm always skeptical of saying absolutely yes, always on this kind of stuff, because you can always find strange cases. But in general, yes, combinatorial problems can be translated into a graph problem. Okay, good. Then different kind of optimization is this convex programming. And for instance, let's say that there is a company that operates multiple warehouses, and you have to supply goods to a network of retailing stores. And then the goal is to ship from each warehouse to each one of the stores, minimizing the total transportation. If I have a nice picture of this, I don't have, but yeah, you can imagine this. So warehouse distribution problem. Um, yeah, probably something like this. Okay, so you have multiple warehouses, so not only one of these, and you have multiple stores, and then how much, so what is the capacity of each one of the warehouses, and what is the demand of each one of the stores, and where, so this one should be supplying this one, or this one should be supplying another one that is here, okay? So my goal is to minimize this, the cost of distribution. Okay, so we are here. And then we have given this example as an example of convex. So convex refers to the convexity of the solution space. So the objective function is convex, and convexity is this thing that if you have a set and you have 2 points, and you can see that the line that connects those 2 points, the line is fully contained within the set. Okay, so this set is said to be convex, and this set is non-convex because this part of the line is outside the set. So this problem in particular is convex. It can be proved to be convex. Convexity is not something easy to prove, but some problems are convex, and we will give you some rules of when a problem is convex and when it is not. So here the objective function is linear, so it is linear this way that we defined before, C transpose X. So it is linear, and if it is linear, it is convex. And the constraints are also linear, so they are also convex constraints. And then if the constraints are linear, the feasible region is a convex polyhedron. So this actually you have. Let's look at the constraints first. Okay, so what is our problem? So our problem is how much should I ship from warehouse I to store J? Then what is the transport cost from I to J? What is the supply at warehouse I? So what is the capacity of I? What is the demand of the store J? So I have to minimize the total transport cost. So the total transport cost is you have to multiply the cost from I to J for all possible I and J's times how much you are transporting. But then what you are transporting from I, so you are transporting from I to all possible J's. So the sum of all possible J's has to be smaller or equal to the warehouse capacity I. And then all the stores have to be supplied. So what you transport from I to J, sum over all warehouses, has to be larger or equal the storage, the store demands. And then all the transportations have to be positive. So you see, these are linear constraints. These are linear constraints. And this is a linear goal function. So if everything is linear, then this is a convex problem. And this kind of constraints here, you can translate them into here. So linear constraints. So a linear constraint is something like C, so constraint I, so this is a vector, if X is smaller than something. Okay, so this is a line. So this is a line here. And then let's say that the side that is smaller is this side. Okay. But then I have another one. Let's say that this is C1. This is C1. And then I have C2. C2 transforms X smaller than B2. This would be 1. This would be 1. Okay, now I have another constraint here. It's a vector. So this other vector is this one, and this is the side of the constraint. And then I have another one. 3 suppose X more than 3. And you keep adding more and more constraints. And what I'm trying to convey here, the idea is that the feasible region is always a polygon. So this feasible region here, something else here, that you remember. So all this region here must be a polygon. And it is a convex region. This is also a polygon, but it is not convex. So if you have a set of linear constraints, the feasible region has to be a convex polygon. Okay. So this is our case. And then there are some special cases, there are some special algorithms that for convex problems, they are very efficient. They don't look all over the screen. They just look at the corners of the polygon, and they find very efficiently those corners. And then actually convex programming has a hierarchy of other problems. So all these problems are complex. And in convex programming, something nice is that they always have a global minimum. And it is very easy to find, or relatively easy to find, a global minimum. Non-convex problems can have multiple local minima. And it is not guaranteed that you will find easily the global minimum. So this feasible region here is non-convex, because if I take 2 points here, the line is not fully contained in the set, and then finding the minimum in this function is much more difficult. Okay, so all these problems are convex. The simplest one is the one we have presented, that is linear programming. Linear programming is a particular case of convex optimization, but there is another one that we will also see. So quadratic programming is more general than linear programming. Actually, linear programming is a particular case of quadratic programming in which the quadratic term is zero. And then second order form programs, semi-definite programming, conic optimization. You see, each one of those are a particular case of the other one, and all of them are convex programs. Okay, so the most general convex program is this one, so it is minimizing with respect to g and with respect to x, subject to these constraints, inequality and equality constraints. So far, it is the same as the nonlinear program, but there are some extra assumptions. The function f is convex, the inequality constraints are convex, and the equality constraints are affine. And the definition of affine is this thing. So it is a vector times the x vector plus some constant. Okay, so then if all this is fulfilled, then this problem is a convex problem. And if it is a convex problem, then the feasible set is a convex. Every local minimum is also global minimum. This is a very nice property. Every local minimum is a global minimum. So if you convert somehow to a local minimum, you are guaranteed that it is a global minimum. This is an extremely nice property. And as I said before, there are efficient algorithms to find these local minima. And these are some of them: gradient descent, interior point methods, and some of the relatively important special cases, linear programming, that we will have only a lecture on linear programming. Linear programming is a particular case of convex programming. So if you find a local minimum in a linear program, you're going to think that that is the global minimum, quadratic programming. So there are a family of methods of programs that are particular cases. Any question? No? Okay, so let's see other kind of problems, these quadratic programming problems. So let's say that you are an investor, you want to allocate, you have an amount of capital, and you have to allocate this capital to different assets so as to minimize the risk. And the risk, we will define it as the variance of the portfolio return while achieving a desired expected return. So actually this problem is called the portfolio optimization, and the solution we will see is called Markowitz model. Markowitz was a Nobel Prize in economy. Okay, so which are the variables that we can tune the fractions of this capital that are assigned to each one of the assets. So let's say that you have n assets, and each one of these n assets has an expected return. So if you collect all of them together, then you have a vector, a return vector. And these assets are not independent. So for instance, there are some assets that depend on each other. If you are thinking of investing into oil companies, all oil companies, they're independent in a way, but they also have an underlying thing, that is the oil itself and the price of the oil, that makes them dependent. So there will be some covariance between the returns of the different companies, and you encode that, or you measure that covariance, and you put it into a matrix sigma. And then you have an objective of how much I want to, what is the return, minimum return that I want with these investments. Then how can I formulate this problem? So I want to minimize the risk. So minimizing the risk is minimizing the portfolio variance. The portfolio variance is this thing, X transpose sigma X. You have had multivariate Gaussian. Have seen the multivariate Gaussian before? I think so, no? Multivariate Gaussian? No? Oh, wow. Okay. So let's see the let's first look for a picture. A multivariate Gaussian is something like this. It's very close to this picture. So this is something like this. So the Gaussian, you know, right? So it is kind of bump in one dimension. So the multivariate Gaussian would be kind of bump in 2 dimensions or in n dimensions. So, and in every dimension, you have a different width. So here you have a larger variance than in this direction. And the covariance somehow rotates this matrix. So the covariance matrix of this example that they are showing there would be a diagonal matrix. But as long as the covariance matrix is not diagonal, then this Gaussian would start to rotate. And the formula is okay. So forget about this normalizing constant exponential, but the interesting part is here. So you have the vector minus the main transpose, and then sigma minus 1x. So somehow you see that the covariance of the variances are related to this kind of multiplications, x transpose sigma x. The reason why it is sigma here and sigma minus 1 here, it is because there has been change of variables. So this is the covariance of a change of variables. But you see that this kind of things, x transpose a matrix and x, appears when you have the multivariate Gaussian. Okay. Then this is the variance of my portfolio, and I want to have a minimum expected return R0, and then the expected return will be the expected return of each one of the assets times the fraction of my money that is on that asset. So this sum has to be larger than something. And then there are some other constraints, that is the sum of all xi's has to be 1, that is all my capital is invested, and all my investments have to be positive. And that in the technical side, actually, that is called short selling. Actually, you can sell something without having it, and xi would be negative. Okay, but let's do normal investments in which they are positive. So this is our problem. And now we see somehow this is this kind of expressions. They are the multivariate equivalents of squares. So somehow you get x squared, okay, and sigma would be the coefficient of the square. So quadratic programming in one dimension, you would expect something like this. So if you don't know anything about multivariate, I ask you what is quadratic program, you would say it's something minimizing something like that. The general quadratic form. So the equivalent in several dimensions would be something like this. So x transpose a x plus b transpose x. So vectors. This would be the equivalent. Okay, so this is a quadratic programming problem. This term is quadratic, and then I have my feasible constraint, my feasible region. So in general, the quadratic programming problem is something like this. And for convenience, we have added there the 1/2. You can always get it from Q. So if you don't have 1/2, you take a factor 1/2 from Q, and then you have Q prime, and then you have the 1/2 in front. Actually, why don't we have the constant? Here I have omitted this constant. Why don't we have this constant? Does it change anything if we add the constant or not? So think of this. So we are minimizing with respect to x, and we are looking for the x that minimizes this thing. So C does not depend on x. It does not depend on x. The x that minimizes this one is the same as the x that minimizes this one. Okay. Okay, so the general quadratic programming problem is this one, and then we have the feasible region, the constraints, standard constraints. So some inequalities, some equalities, and we said that quadratic programming is a particular case of convex programming. So if it is a particular case, not all Q's are valid. So only some Q's. This is always convex, but this may not be always convex. So the condition to be convex is that Q is positive semi-definite. This is something you know, no? On linear algebra, positive semi-definite. So it means that all the eigenvalues are either 0 or larger than 0. So are 0 or larger than 0. And it is written in that way. So look at the sign. The sign is this one. Okay, so if Q is not positive semi-definite, then the problem is not non-convex. And this problem, even if it is a quadratic problem, it is not quadratic of the family of convex problems that we have. Okay, good. More problems. Conic programming. So conic programming, let's see. An investor wants to allocate the capital, so the same investor as before, so wants to allocate the capital for several steps to minimize the risk, so far almost the same. But now assumes that the asset returns are uncertain within a confidence region. So now, before we took the returns, we took the returns as the expected return, but now we are considering a bag for each one of the returns. And the goal is to construct a portfolio that performs well, even in the worst case conditions. So how to translate that? Okay, so X will be the portfolio weights as before. Mu will be the nominal expected returns, but there will be a covariance on top of that. So now we will put the expected return here in the goal function. That it is different from before. Before, the expected return was one of the constraints. Now it is something that we want to optimize. We want to maximize this, but we want to maximize the expected return, but we want to minimize the variance. So this thing somehow it is this one was the same as this one. That's before. This one. Let's get you. So why this thing is the same? Okay. So we have written, so we have written sigma 1 half x, then the square. Okay, so what is this? So the norm of a vector, the norm of a vector in general, square norm of a vector is x transpose x, right? Okay, so this will be sigma half transpose sigma half x. And now we have two terms, this transpose and this one. Okay, so now transpose of a multiplication is x transpose sigma 1 half transpose. And then we have the other term, is unchanged, sigma 1 half x. Okay, but now, so now this is, I will use part that we change. Okay, so this is kind of clear. So this matrix sigma is semi-definite. And this implies that it's symmetric. This is a symmetric matrix. And then if it is symmetric, then these two operators can commute. So this is the same as sigma transpose. If it is symmetric, this one is also symmetric. And they can also commute. Through both things, I said that. And then this is the square root of a matrix times the square root of the same matrix. This is sigma. So writing this or writing this is the same. So let's look at the goal function again. So I'm trying to maximize the expected return, but then minimize the variance. And then I have to give weights to how much more important is the expected return for me with respect to the variance. And this is this gamma. So gamma controls how much more important is this term with respect to this. If it is very important, I will set it 2, 3, 5, 10. But if it is not important, if it is not important at all, you can put it to 0, or you can put it to 0.1 or to something. Okay? So gamma balances how much more important is the variance with respect to the expected return. But now you see that we have a different formulation, and then we have our usual constraints. And there is a difference between the quadratic problem that we had before. The quadratic problem here was using a plus. Here we have first the linear term minus something that is positive. Okay, and that is called conic programming. So in a conic program, the general conic program is like this: C transpose X, subject to this, subject to some code. Okay, so K is a cone, and there are different ways of defining your code. And you can imagine that we can, using some tricks as the one we use with the slack variables, you can transform this problem to this one. That we will learn. Okay, yeah, we are going to. Okay, so we want to maximize this, and this is the same as minimizing this thing. And then the trick here is, okay, I will call this thing, I will call this T. If I call it T, now this is a linear term. And then what I will say is that this thing has to be smaller than t. So this thing can be smaller or equal to t, and then I have transform my quadratic problem into a linear problem. That is a trick. Any question to here? No? Okay, more problems. So now we will include time. Yeah.
I don't get, where do you get that T from?
The t is an auxiliary variable. So it is an auxiliary variable that will help you
So
to transform a quadratic problem into a linear one.
So T,
It is a new variable.
yeah, but it is the norm of that thing.
No, the norm of x has to be smaller than t.
Okay. And what is that?
Because you want to transform this term into something linear, then you can use this trick, right? So I will say this has to be smaller than t, and then I want to minimize this thing.
But why would you want to be smaller?
Because if it is if I want to minimize something, that depends on the norm. I want the norm to be as small as possible,
Okay.
right? So you see that this trick of introducing auxiliary variables is very much huge. Okay, now we will introduce time. Yeah. So we will introduce time, and then we will have a collection of programs. This dynamic programming is not a single optimization problem, but it is many optimization programs at the same time. So let's say that a store must decide over an horizon of t days how many units of product to order each day to meet the customer demand. But this customer demand is uncertain, so you don't know how much you will get every how much of that product will be demanded every day. But what you want is to minimize the total cost, and the total cost include the ordering cost, because it has to be transported, and maybe even for every order I have to pay something, or I have to pay someone who is making the order. So there is a fixed charge per order. Then the holding cost. So if I have a given amount of product that I'm not selling, having that into my warehouses or my shelves, they cost money, and the shortage cost. So if I run out of the product and someone comes to buy it and I don't have it, I'm also having a cost, that is the cost of not having the benefit of selling them. So this is the total cost that I want to minimize. And the thing is that, and why this is called dynamic programming, is that what I do today will have an impact on tomorrow's state. So there is a kind of, I have to solve for every day. I have to solve how much I want to request, how much I want to order, and there is a dependency on every day. So I will define two variables. One is the current inventory, so the inventory at the time t, and the quantity order at day t. That is my action. That is so this is the state called S. This is my action called A, and then I will have a random demand. So this random demand, I will call it BT. I know the distribution, but I don't know the particular value every day, but I know the distribution they're coming from. And then I will somehow encode the whole cost. So the cost will include ordering, holding, shortage, and I have to update my state. So my state tomorrow will be the state today plus my action today minus my demand today. And this demand is a random variable. And my actions, I have to choose my actions. So I am minimizing this with respect to my actions. And then all these dynamic problems somehow they're solved in this way. So the standard finite horizon dynamic problem, so the time doesn't go to infinity, but it goes to some maximum time t, capital T. They're divided into smaller subproblems. So these smaller subproblems somehow is the value. So I can consider set of states. So my state here is how many units I have per given problem. So let's say my maximum is 1,000. So I have all possible states between 0 and 1,000. And then I associate a value to each one of the states. So this value, maybe probably if I don't have anything, probably that has very little value because I even it has a negative value because I'm losing those cells. So I have a negative value. And then if I have 1,000, I have to store a lot of those products. So probably maybe that is also negative, and my value is something like that. So, but I don't know. So I know more or less how it should look like. I don't know exactly what curve is that. And I will define the curve in this way. So the value at time t of a particular state is, let's say that I have at this moment I have the state S, and I take action A. Action A, the actions here, I will order 10 units every day, or I will order 100 units or whatever. So I am in this state and I take that action. And that state and that action will bring me to the next state. And we already know this problem, how to get to the next state. Even this state and this action, the demand today, I know how to go to the next state. So that will give me, so that equation that we saw before will give me the state transition function. So in general, we have some state transition function. And I know that if I am in this state and I take this action, I will be in this action in this state next time. And I can calculate what is the value of that state. So this is st plus 1. So this is the next state. And then I can compute what is the value of that next state because I have this curve. But I don't have it yet. I don't have it yet. But once I have it, I can evaluate what is that value. And then there is a cost associated to taking this, being in this state and taking this action. So the thing is that I have to minimize this value or maximize that value. So here it is written as a minimization because in general we write things as minimization, but in the problem before we want to maximize that or minimize it. Okay, so I put it as well. Okay, so then I want to minimize this. The value is positive with respect to all my actions. And then we will solve it backwards. So even just the day before you are supposed to plan for a month, just the day before the last day, it would be relatively easy to find what is the value of each one of the actions. So I could, given the value of each one of the actions, I can calculate what is the value of each one of the states. And if you have solved it for the day 29, then you can solve it for the day 28, and then you can solve it for the day 27. So actually, you see that this is a recurrent problem, which the day today is a function of what will happen tomorrow. And then you go from the end towards the beginning of the period. We don't see how to solve this thing yet. We will do it later in the course. But you see that for every day you have an optimization problem. So you have a collection of optimization problems, and which is the best action that you can have in every day. So these problems are much more complicated than the ones that we were seeing here. Even if the mathematics looks very fancy with matrices and inner products, actually this is much more complicated to solve. Reinforcement learning, have you, do you know what reinforcement learning? Reinforcement learning is one of these problems. Okay, then time, okay, time for a break. Okay, so then let's move on to different kind of problems. Next one will be called stochastic programming. So it is kind of similar problem to the one we had before with dynamic programming. So a store that has to decide how much more than every day. But now we will formulate it for a single day. Okay, so for a single day, we have to decide how much to order. And if we order X, that will be some associated cost with, for the transportation of that X, or that is CX. So we want to minimize that transportation cost plus something. Okay, that something has to do with the holding cost and also with the penalization for not having product in somebody comes to buy. So let's see. So let's say that the demand today is V, and this will be a random demand. And then the holding, what is the holding cost? The holding cost for just 1 day. For just 1 day will be the holding cost of H per unit times the part that we are not selling. So we order X, we have sold D, and then X minus D is the one that we have to store. And if we sell everything, then or the demand is higher than what we order, then this will be negative. So it is the maximum between what we have not sold and sell. And then there is a penalization for the unmet demand. So the unmet demand is D minus X. So if D is larger than X, then D minus X will be positive. And otherwise, there is no unmet demand, will be zero. Okay, so this maximum here, they take care of whether you have sold everything. But the demand is random. So if the demand is random, then you don't know this is a value that depends on a random value. And then the best thing can do probably is just take the expectation with respect to the distribution of the data. And then you want to minimize that. So minimize the transportation cost plus the storage cost plus the unmet demand cost. So these problems in which one of the variables is random, you have to minimize, taking into account the distribution, the statistical distribution of that variable. It's called stochastic programming. And in general, they can be formulated in this way. So it is minimizing with respect to something that you can control, some function, and this function is a function of what you can control and what you cannot control. And this part that cannot be controlled will have some statistical distribution, and then you minimize the expected value of that goal function. Then different kind of problems are this multi-objective programming. So far we have only had one goal function to minimize or to maximize. What if we have multiple functions to minimize the function? And here is an example. So let's say that you are in a car company. These car companies designing new cars, and they want to optimize multiple objectives. So on one side, they want to maximize the fuel efficiency. So how much miles per gallon you can run on this car, or to minimize the energy consumption. You want to maximize the crash safety, so impact resistance, structural strength, and so on. And you want also to minimize production cost. The problem is that these three objectives, they are conflicting with each other, because probably if you want to increase the safety, you have to use better materials, and better materials means higher cost, and also maybe even higher weight. Maybe this higher weight, then your fuel efficiency will go down. So there's a conflict in all this. So in general, we want to minimize, in this example, three goal functions at the same time. So for minimize fuel consumption, maximize safety. So maximizing safety is minimizing minus safety, and then minimizing production cost. Okay, so in general, we will have k functions to minimize. So our goal function minimize will be a vector. So far, they have always been scalar functions. Now they are vector functions. And there are some variables that you can control, and that will be a physical region. And each one of these functions will be a scalar function. Okay, so now there is not a single optimum. So far we have been discussing local minima, global minima. For convex problems, the locals are global, but there was a point that was global. What will happen now is that there will be a region of points that are as good as the rest. So there will not be just a point, but there will be something called the Pareto front. So the Pareto front, all points, you have to decide by some other means, because all points in the Pareto front, they are said to be non-dominated. Non-dominated, what it means. So if you change, let's say that I am in A, I have chosen A point, the solution A. F2 is very small, but F1 is very high. And there is no way that I can improve F1 without sacrificing F2. If I try, okay, this F1 is terribly high, I want F1 to be smaller. But if I want F1 to be smaller, necessarily, I will increase F2. So at all points in this Pareto front, they fulfill this property. The point is in the Pareto optimal front if there is no other feasible point such that this is the point at the Pareto front, such that you are improving one of the variables for all the criteria, and there is one for which it is better than before. So it is better or equal for all except for one that you are improving. Okay, so all these points fulfill this condition. Why this C is not in the Pareto front? Okay, let's say that I say, okay, my current solution is C. So if my current solution is C, I can still go to B, and I'm getting better in F2, and I'm not getting worse in F1. Okay. So I can find a point in which I'm as good as I was in F1, and I'm better in F2. So B is better in F2, and the same for D. So you can go down in F1, and still you're not sacrificing anything in F2. Okay, so this is all your physical region. So at the Pareto front, you have to sacrifice, you have to decide whether it is better to have F1 or F2. But outside the Pareto front, you can get better in at least one of the criteria. Okay, so that didn't happen with the previous optimization, but it now appears, this concept appears in this multi-objective optimization. So if we want to maximize several criteria at the same time, there will be a point in which you cannot get better without sacrificing any other of the criteria. And then you have to decide for your company where you want to be. But from the point of view of the optimization criteria, all these points are equally good. Okay, any questions?